Greetings everyone, it's me, Dolly the Sheep. Today me and Dolly AI will tell you about living sheep bioreactors to produce an important protein called coagulation factor 9 in transgenic milk. Hemophilia B is characterized by coagulation factor 9 deficiency, and as I will show you with the help of Dolly AI, severe cases that correspond to half of hemophilia B patients can be life-threatening. Do you want to know more? Then keep on watching and welcome to the genetic basis of stuff and things. Hemophilia B can cause intracellular and muscular bleeding, joint bleeding, and nosebleeds. But why are coagulation factors so important? Well, every time you have an injury, a palate plug is created, but on its own is not enough. The coagulation cascade, made of several coagulation factors, including factor 9, creates a fibrin mesh that stabilizes the plug and forms a clot. A deficiency in factor 9 leads to a defective coagulation cascade and an inadequate formation of the fibrin mesh. So, without factor 9, the blood cannot clot properly to control the bleeding. Gene F8 in chromosome X encodes for coagulation factor 8 and gene F9 encodes for coagulation factor 9. Since males only have one copy of the X chromosome, a mutation in gene F8 will cause hemophilia A and a mutation in gene F9 will cause hemophilia B, so they are the ones that are affected by the disease, while females are usually just carriers. There are two options available. The first one uses coagulation factor 9 derived from human plasma. However, this method can also transmit pathogens like HIV and hepatitis, making it a little risky for patients. The second option is recombinantly producing coagulation factor 9 in mammary cells. However, they can be very expensive and have low yields. So, we need to come up with new solutions to treat hemophilia B. The solution are transgenic organisms. They have a foreign DNA sequence in their genome, and thanks to them we can produce medicines, better crops, and disease-resistant animals. Transgenic farm animals have become quite popular. They have been used to increase meat and milk production, to produce organs or organoids for research and xenotransplantation, and to create living bioreactors to produce important proteins, just like coagulation factor 9. Coagulation factor 9 needs several post-translational modifications like beta-hydroxylation, glycosylation, and gamma-carboxylation before it can become active. Mammalian cells are capable of making these post-translational modifications, but like we mentioned, they are quite expensive. Why use the cells when you can use mammals at a lower cost? They can also produce complex proteins and secrete them in their bodily fluids. If we target gene expression to the ovary in chickens, we can express the protein in egg whites. If we target it to the bladder, we can express it in urine. And if we target it to the seminal vesicle, we can produce it in seminal plasma. Luckily for Dolly AI, the most used one is milk, because milk is produced in large quantities in different animals and the mammary gland can perform all necessary post-translational modifications. Sheep are our bioreactor of choice because they reach lactation relatively fast, so we have a couple of volunteers that wanted to contribute to science. We must target gene expression only to the mammary gland. If a foreign protein enters the bloodstream, it can cause a lot of undesired effects. Luckily for us, several genes encode milk-specific proteins. One of them is the beta-lactoglobulin or BLG. Its transcripts are abundant in mammary tissue, so we can use it to drive high levels of expression of foreign proteins into milk. We use the human DNA that encodes for the protein. To take out the intron sequences and make it shorter and easier to manage, we convert it to cDNA by reverse transcription. And now, using restriction enzymes, we cut the part that encodes for the protein. We insert it into the 5' untranslated region of the first exon of a segment of the BLG gene that includes all the specific regulatory elements that control the temporal and spatial expression. So now we have created our fusion gene directed exclusively to the mammary tissue. Our gene will be transcribed into a potentially bisynchronic mRNA that can be translated into both proteins, which will be secreted into the milk. To create our living bioreactor sheep, thousands of copies of the fusion gene are microinjected into the pronucleus of a fertilized egg, and then it is surgically introduced in the reproductive tract of a surrogate mother. The surrogate mother had 2 daughters, each one with around 10 copies of the fusion gene. Once they reached lactation, it was time to assess coagulation factor 9 in their milk. We were able to identify active coagulation factor 9 in sheep milk. However, the quantities are still too low compared to human plasma, and we don't have enough to purify for therapeutic purposes. Not having the natural intron sequences could have impacted expression in transgenic animals, so using the human's DNA could be the best option for the future. Even small amounts of the protein could be enough to improve the patient's life. There is still a lot of work to do, but we are in the right track to create transgenic milk that can improve life all around the world. Thank you for coming along, and stay tuned for more scientific discoveries.